Okay, hello everybody, welcome to the 699 presentations. For the benefit of the students, I would like to explain that as a part of our graduate program, we ask students to undergo some research experience. And so they have to find an advisor and develop a research project. What we are going to see today is a result of the first research project by the three students who are sitting over there. The three talks, each talk is going to be 20 minutes, and then we will have 5 minutes for questions. All right, so we start with the first one by Ashley Chontos. She changed the title, Asteroseismology of Kepler exoplanet host stars.
Thank you, Roberta. So good afternoon, everyone. Thank you for being here today. My name is Ashley Chontos, and for my first 699, I worked with Dan Huber on asteroseismology of Kepler exoplanet host stars. So I'm not going to really spend too much time talking about Kepler, as I'm assuming everybody in this room has heard what Kepler is. Its main science objective was to detect exoplanets, but more specifically to determine the frequency of habitable Earth-like planets. But it turns out that Kepler is also a great machine for asteroseismology. So first of all, what is asteroseismology? Asteroseismology is the study of oscillations in stars. We use the term solar-like oscillators to very loosely define any stars that have oscillations which are driven by the same mechanism as that found in the sun, which is convection. So if you took a look at this HR diagram of taken from exoplanets.org, updated a couple weeks ago, so this is all current known exoplanet hosts, and kind of have a broad range here to define solar-like oscillators, and this involves a subset of evolved stars which still have convective envelopes. So oscillations can be defined by spherical harmonics, where radial order n is the number of nodes from the surface of the star to the center of the star, and the spherical degree is the number of nodal lines on the surface of the star. But in general, it's really difficult to resolve the surface of distant stars, making these higher spherical degrees difficult to observe. And there's also another effect happening here, is that oscillation amplitudes scale with luminosity. So for solar-like oscillations, they generally have lower signal-to-noise cases. Solar-like oscillations happen on the order of 5 to 10 minutes, thus emphasizing the need for very high cadence observations. So why do we care about asteroseismology? Asteroseismology is currently the most accurate and precise way we can determine fundamental stellar properties. It has successfully measured stellar masses and radius to within 7 and 3% respectively. It is also currently the only way we can measure the stellar properties for field stars at this precision. So if you take a look here, this is a power spectrum of the sun taken from Tim Betting paper in 2011. We have a full power spectrum of the sun on the top with a zoomed in version on the bottom. And as you can see, an oscillation doesn't happen at one frequency, but in fact over a range of frequencies. And this is actually due to the stochastic nature of the excitation. So solar-like oscillations are approximately Gaussian, where the frequency corresponding to the peak height of this envelope is frequency of maximum power, or nu max. And then at the bottom there, you can see this periodic spacing, or what we call characteristic frequency spacing, represented by this. And as I was saying before, the higher order degree modes are really difficult to observe. And in the case of solar-like oscillations, we can easily observe both the L equals 0 mode, or the radial mode, and the L equals 1 mode, which is our dipole mode. And it turns out that these two adjacent modes are roughly approximated by delta nu over 2, and I'll explain why this is important in just a little bit. So back to these two seismic parameters. If we have an effective temperature of the star, we can then easily calculate the stellar mass and radius using these scaling relations. So why do we care about this in the context of Kepler? So on the left here, we have two very different systems. On the top, we have a gas giant orbiting around a giant planet, and on the bottom, we have an Earth-like planet orbiting around a solar-like star. On the right, we have their measured light curves, which is relative stellar brightness as a function of time. And as you can see, these are identical light curves for two very different systems. So knowing the star size is really important. We only know our planet as well as we know our star. So with Corot and Kepler, which both provided high precision photometry, it really revolutionized the field of astroseismology. And specifically for Kepler, there's now an important synergy between exoplanetary science and astroseismology. So in the top left here, you can actually see a single transit for Kepler 36. In the red is the best fit line for the transit. And from this transit depth, we can actually calculate a ratio of the radius of the planet to the radius of the star. And with the entire time series, we can do a Fourier transform and look for power spectrum, which we can see right here. And based on those two seismic parameters, we can then determine the stellar mass and radius. And by combining those two, we get a really precise planetary radius. So we're really doing two different sciences with the same set of data. So the motivations for this research, most planets detected today are via indirect methods, so we only have relative planet properties. And because astroseismology is the most accurate and precise way we can measure these stellar properties, in the special case that we can find oscillations around exoplanet hosts, we get the best characterized systems to date. So there's two previous works on seismic Kepler hosts. The first was by Dan Huber et al. 2013, using roughly half of the Kepler data, found 77 seismic hosts. And then more recently, we have Mia Lundquist et al. 2016, who used all of the Kepler data and found 102 seismic hosts. However, this was for a very specific science case, and they didn't include all seismic parameters. And even after these two publications, there was a re-release of short cadence data by this short cadence bug that was discovered. So what we wanted to do is go back through the new data and see if we can find new seismic hosts, as well as confirm oscillations in already known hosts. So the main goal here is a definitive catalog of all seismic exoplanet hosts. Moving on to our methodology. We decided it would be advantageous to create new software and add in more tools in order to be able to detect oscillations in lower signal-to-noise cases, as we knew all of the low-hanging fruit or oscillations with the largest amplitudes would already be detected. And I apologize in advance because I'm going to kind of rush through the methodology, which is really important because I spent a fair amount of time developing this, but I have a lot of exciting results to show, so please feel free to ask questions about that in the end. So, I'm sorry with that. I present quakes. It's quick characterization using astroseismology of Kepler exoplanets and stars. So we use quakes to find star quakes. So quakes is a several-step process with 9 steps in total. The first 6 steps here that I list are all in the time domain. So I don't have time to go through the individual steps, but the two plots I want you to really focus on is this raw light curve here. So this is of Kepler 7. Kepler 7 is a solar-like star that has a hot Jupiter orbiting, so you can kind of see these transit features at the bottom here. And then I want you to look at this light curve over here. So this is what it looks like after we've done all of these steps over here. And then if you look up to the top here, this is actually the same plot as this. Well, it's not the same plot. So this is what it would look like had we not done any of these steps. So this would be just the high-pass filter of this raw light curve here. And it's not on a different scale here. There's actually some funky data over here, and there's a bunch of outliers that are scaling it this way. So I explained the last 3 steps by showing this really ideal power spectrum. This is actually a perfect example of the low-hanging fruit that I was talking about. These are not the power spectrum that I get to look at. So this is Kepler 21. In this main plot, we have the power spectrum here, which is power density as a function of frequency. And for the non-astroseismologists in the room, which is basically everybody, I've included periods rounded to the nearest minute here for reference. So in the black, we have our original power. And then in the red here, we actually have the power smoothed over 1 microhertz. Now we use smoothing filters to help reduce the noise floor, making oscillations easier to detect. So if the signal is real, we don't expect these smoothing filters to damp out the oscillations. And And then for based on current stellar properties, we can actually estimate a value for nu max, which is shown by this blue dashed line here. And then, as I said before, because the stochastic nature of the oscillations, we have oscillations through a broad range of frequencies, which is shown by the shaded region here. So using this smooth power in this shaded region, we then calculate an autocorrelation. And now going back to those two frequency spacings that I was talking about before, we have delta nu and then delta nu over 2. So when we correlate the power against itself, we expect to see peaks at delta nu and integer multiples of that, which is shown by the blue dashed lines here, and then also delta nu over 2 and integer multiples of that as well, which is shown by the red dashed lines. So if we see strong peaks in and around these values, we have pretty strong confidence about the detection. Now I know it's quite obvious here that there are oscillations, but I will show why in a few minutes, why this autocorrelation is very important to quantitatively confirm the oscillations that we think we're seeing. So here's a summary plot of our results. On the left, we kind of have the asteroseismologist version of the HR diagram, which is also called the Kiel diagram. So you have the log G on the y-axis instead. And this is, so all currently known exoplanet hosts is shown in gray. And for in black, we have the previously known hosts in which we were able to find oscillations in with the new data. And then, however, the oscillations that, the previously known hosts that we weren't able to find oscillations in are represented by this little blue population down here. And perhaps the most exciting, the new ones, those are shown in red up here. So on the right here, we have our planets that are orbiting around these stars, and you can see it's not a one-to-one because Kepler has demonstrated that planets are more abundant than stars. The colors signify the same, they have the same meanings. And this is planetary radius in Earth radii as a function of orbital period in days. And you can see that the Kepler population of planets it fully explores really this parameter space. So in total, we have 14 new seismic hosts and confirmed oscillations in 92 known seismic hosts for a total of 106 seismic Kepler hosts. So on to a few of our more interesting new detections. So I'm going to start with the highest signal to noise case for us and kind of work our way down so we can convince you of these oscillations. This is KOI-4. KOI-4 is an evolved subgiant believed to be hosting a hot Jupiter. In the black here, you can kind of see like a roughly Gaussian shape. And then when we do a heavier smoothing filter down here, you can still see some strong peaks. But then when we calculate the autocorrelation, it becomes quite clear. We've also had two independent collaborators that confirmed oscillations in this frequency range as well, and I'll explain why this is important in just a few minutes. So the next one is KOI-94. KOI-94 is a confirmed 4-planet system around a solar-like star. I know this is a little bit messy, so I'm going to take a few steps back and walk you through the process that I would go through in order to find oscillations. So first we plot the power spectrum in log-log scale. And the idea here is that it would concentrate the oscillations and kind of form like what you see is like a little bump. If that isn't obvious to you, I've actually plotted also that very ideal case that I showed before, and it's a little bit more obvious here. So I would have picked up on that because it's a little bit more concentrated than the rest of the power spectrum. And then in a linear scale, you can then begin to see the structure right here. And if you zoom in, you do see some power access. And then when we compute the autocorrelation, again, this is pretty strong. We have pretty strong confidence about the oscillations in this chart. Okay, so this is a really difficult one again. So I'm going to go back out to the log-log plot. This wasn't really telling at all. And then we look at this, and this one's kind of hard to see as well. So this star is actually our very first detection. I also think this is when I was a little bit more patient and would go through these power spectrum like through the entire frequency range. So I happen to see kind of like 4 peaks here. And then when you zoom in, there's something you notice, there's actually kind of this like consistent spacing. And usually if I saw this, for 3 or 4 consecutive modes, Then I would use that and calculate an autocorrelation, and sure enough, I think we see oscillations in this star as well. So KY302 is really interesting. This is also another evolved subgiant, but the reason it's so interesting is because it's hosting a sub-Saturn-sized planet. So not only do we not have this planet type in our solar system, but if we look at the most current Kepler occurrence rates, actually done by our very own B.J. Bolton, released this year, this planet type is orbiting in less than 1% of the stellar population. So we actually were able to get some spectra from characterized. So hopefully we'll be able to get a precise mass and radius calculation of this pretty interesting planet type too. So I'm going to spend the rest of my presentation talking about perhaps our most exciting result, which is KY4. And KY4 is a perfect example of why asteroseismology is so important. So when Kepler first launched in 2009, the first 3 transiting planets were actually known from ground-based observations. So thus designated the first 3 KY numbers for Kepler objects of interest. So that would make KY4 Kepler's very first planet detection. So the initial Kepler input catalog, or KIC, were classified using broadband photometry. While they were very useful, sometimes it could be significantly inaccurate. So this star was actually initially listed as a solar-like star, and this primary transit depth would have given us roughly a Neptune-sized planet. However, when we observed a secondary eclipse, it didn't make sense. So they listed KY as a false positive. However, when we were doing our seismic analyses, we estimated we estimated roughly a stellar radius of 3 solar radii. So this is an evolved subgiant consistent with a Jupiter-sized planet. And this actually makes sense with the secondary eclipse, but that still doesn't mean that the planet is real. So we reached out to Dan's collaborator Dave Latham and the rest of his team to collect some RV data. And within a week, we actually had this beautiful radial velocity curve confirming the planet. So this is really exciting. And with our seismic stellar mass, we were able to confirm that KY4 was in fact hosting a very massive hot Jupiter planet. So this research was done really quickly. So quickly that when we presented at the Kepler K2 Science Conference at the end of June, we actually attached this plot kind of right next to my poster there. This is a very excited Ashley Chontos in the background. This is our collaborator, David Latham. Again, this is just us celebrating the discovery there. So Kepler's first planet to be discovered, and one of the last to be confirmed. This is also kind of important because Kepler officially ends on September 30th, so it was nice to get this confirmation in time for that. And if you haven't already noticed down at the bottom, I don't know if you can actually see this below the table, but we are working on a separate paper, especially for KY4, and we hope to have that published by the end of the year. So this first 699 diverged into 2 very different projects. We are currently working on papers for both of them, and this also leaves a lot of work to be done. So going back to the seismic host study, I will use an existing pipeline to calculate the seismic parameters for all seismic hosts. And using the scaling relations I talked about in the beginning, we plan on recalculating new stellar and planet parameters for all oscillating hosts. We do have characterized time, and we also have collaborators that are willing to observe targets and do follow up whenever possible. And something I actually didn't mention before, but there's currently no public software that is available to do astroseismic analyses. So we do plan on packaging and releasing quakes so everybody can do asteroseismology. And then for KY4, due to time constraint, I can't really talk about this, but we believe that KY4 is on an eccentric orbit. So we are working on getting more RV data to hopefully constrain this eccentricity. And once we have that, we plan on doing MC&T analysis to retrieve the other system parameters. Because we do have a secondary eclipse, we can calculate the planetary albedo. And they believe that we can measure orbital period decay with Kepler data. So that's also something we can do. So in conclusion, this is the first complete study of oscillating Kepler hosts. since the newest release of data. We've developed new software for light curve analysis that allows detections in lower signal-to-noise cases. We've proved this works. We have 14 new detections, including KY4, which is Kepler's first planet. So we got a planet for free. And there are many future applications. So we have tests flying next year, which will also provide high precision photometry. And it's really helpful to know that we have existing software that we know works. That way, when data does come in, we can kind of hit the ground running, as now everyone in this room now understands why asteroseismology is so important. Thank you.
Two short questions.
Sure.
In your very first step, you say you reduce the large variability, but you didn't say where that large variability comes from.
I'm sorry, for what?
You have these 9 steps where you go through, and the first step was smoothing this large variability.
It was actually, the first step is the quality flag in the pipeline you're talking about here?
Yes, yeah, this one, the first graph on the left.
Oh no, I just wanted to give an idea of what a raw Kepler light curve looks like.
And where is this variability from?
Oh, okay, so this is Kepler when it's orbiting, it does a quarterly turn. So each target is actually read on different CCDs.
Okay.
And thus giving the difference in total flux there,
Okay.
as far as I understood it.
And then maybe connected to that, in your power spectra that you showed, you had these narrow spikes that you didn't discuss, the broadband logarithmic power spectra.
Oh, okay. Oh, yeah, sure.
Yes, so this spike in the middle, what is that?
This one right here?
Yeah.
So this is what we call a lovely Kepler artifact.
Mm-hmm.
We don't know why it happens. It happens roughly around like 350 microhertz. It shows up in the short cadence data.
In every object.
I'm sorry?
In every object.
Yeah, I mean, it's more visible in some more than others. I think you can actually see it in KOI4. You can kind of see it right over there. But yeah, as far as I know, I actually don't know what causes that, and I don't think.
No, it's there. It's a Kepler artifact completely.
Yeah. Well, we can't explain things, it's just a Kepler artifact.
Allow me to go first to the neighbor island. Jeff, you have something?
Yeah, I just had a quick question about whether you tried to inject artificial signal into your data to understand what your efficiency was at finding oscillation amplitudes. You didn't mention, as in this search, what you thought your completeness might be as you search for these seismically active stars. Do you have any idea?
That's actually a great question. And as we were kind of nearing the end of our project and we had our list of our seismic hosts, when we found KOI4, we kind of just dropped that project and, we prioritized KOI4. So we kind of, we still have a lot to do. So that's definitely something that would be interesting in adding in. But it's not something that we've looked into yet. Thank you.
So you mentioned there are 10 false positives in your Kepler. So how do you know if it's a false positive?
Are you talking about the ones where we weren't able to find oscillations within the new data?
Yeah.
So this is something we're actually going to look into. We don't know. So this was from a collaborator, Mia Lundquist et al. Was the one that found these stars. So we don't know if this is an effect of the short cadence bug in this new release of data, or if it's something else. This is something that we're definitely going to look into.
So what's the expected false positive percentage in your Kepler?
I think, I don't know, I wouldn't necessarily call it a false positive. This was just me kind of disagreeing with what someone else was finding, whether or not that's significant, or if it's a result, like I said, if it's a result of the data, we really don't know. We haven't looked into that yet.
Yep.
Could you tell us a little more about your error analysis? You initially lost your power spectrum, you shaded this little region where there's a Gaussian bump. The presence of this Gaussian bump to the uninitiated eye would be roughly 0 sigma, most in the audience. So that's that probably doesn't drive the errors because the errors come from the autocorrelation function. Could you help us understand what they are quantitatively?
We actually, so again, this is kind of going back to what he said. Once we had our list and found these interesting new hosts and found KOI4, we kind of just put this project aside. So once we start calculating the seismic parameters, as I understood it, the noise, at least the noise that we see here, well, actually, this is a perfect example. This is taken into consideration when we determine the precision that we find for the stellar parameters. I'm not sure, I haven't done that yet, but this is something that we will be doing. So when we make the catalog, we will be determining the precisions. I'm actually not sure how we determine those yet because we haven't done it.
So the parameters you list on the right there for the stellar radius of these, you're quoting them to 2 decimal digits. What's the error on these numbers?
These are taken from the NASA exoplanet archive.
Oh, this is not one of your measures.
No, I'm sorry. Yeah, I should have made that more clear. No, these are taken directly from the NASA exoplanet archive online, and just due to lack of space, and it would have been really cluttered, I didn't include their uncertainties, but they're all between 20 and 50% uncertain. So they have pretty high uncertainties on these values, which is why asteroseismology feel really important because we can get them down to within 5 and 10%.
So you think you're going to get percentage accuracy out of those data?
Yes.
So I can talk about, I mean, if you would pick a single peak in the power spectrum and ask is it significant, then the answer is no. But if you take the ensemble of these peaks and calculate an autocorrelation and say how well can we measure that peak in the autocorrelation, the answer is a few percent, and that then propagates into the radius of a few percent. So
how much does it depend on which shaded region you pick in that?
we know roughly how wide the power axis should be given a certain oscillation frequency. So it shouldn't depend, but if you take the entire region, then you're obviously diluting your signal because you're looking at a region where you don't expect to see oscillation. So you pick a region that's wide enough.
Okay, I think we can thank Ashley again